we're going to very briefly go into the idea of dimensions and units. And dimensions and units are very important in engineering because it's how we describe quantities. Quantities like properties, density, length, time. We use units to describe these. So, first of all measurements and calculations have both dimensions and units. They're both there. Dimensions are the physical qualities like mass, length, time, and temperature. And in fact, there are two primary systems for dimensions. One is the mass, length, time, and temperature, and one is force, length, time, and temperature. Now, these aren't totally independent. They're related by Newton's second law. Force equals mass times acceleration. So, depending on what our system is, we might use different versions. Now, the SI units are a mass, length, time, and temperature, where we define kilograms, meters, seconds, and Kelvin, and then the force, a Newton, is described by Newton's second law. However, the British system of units is actually force, length, time, and temperature. We define the pound force, the foot, the second, and the Rankine, and then we define the slug as the unit of mass. English engineering units are a little bit different because we use force, mass, length, time, and temperature. So we have defined units for all of these, but then we have to have some conversion factor between pounds of force and pounds of mass. That's based on Newton's second law. So it's a little bit more complex. We have to have some additional conversion factors. Now, units are the arbitrary names and magnitudes that are assigned to the dimensions. Now, we have to pay close attention to units. We can look at length and we can measure it in feet or miles or meters or whatever we choose to use. And these then are related by conversion factors. There are 5,280 feet in 1 mile. Now, you can often use units to work out how to solve a problem. And when you do homework in this class, I expect to see unit conversions written out in homework. This is very, very important. In fact, there have been some serious accidents that have occurred because units weren't converted properly. In fact, we crashed a lander into Mars because someone didn't correctly convert from meters into feet and it was input incorrectly into the computer code. When we talk about dimensions and units, we have to make sure all equations are dimensionally consistent. Dimensional consistency means that every term in the equation has the same dimensions. So you can only add length with length or velocity with velocity. You can't add length plus velocity. So if we look at these two equations, which one is dimensionally consistent? Well, it's this one on the top. It's this one here. You see here we have length. Here we have velocity times time, which is length. And here we have acceleration times time squared, which is length. So all of these terms have units of length. However, in the bottom equation, this one has dimensions of length, velocity, and length. So here we have an inconsistent equation, and we can't use this equation. It's invalid. Now, some equations in engineering are not dimensionally consistent. One example is the energy efficiency rating for air conditioners. We measure air conditioner performance in the United States in BTUs per hour, which is how much heat you can remove from a building. However, we measure energy consumption in watts or kilowatts. So the EER is the cooling rate in BTU per hour divided by the power input in watts. Now the dimensions are consistent here, but the units are not. A more scientific version would be the coefficient of performance, where we would put the cooling rate in watts and the power input in watts, and we would end up with a unitless number. Now it's important to be able to convert units efficiently from one type of measurement to another type of measurement as we do our calculations. So the conversion itself is actually a pretty simple trick. We just multiply by 1. So if we know that 1 inch is 2.54 centimeters, then we can convert from inches to centimeters by multiplying by 2.54 centimeters over 1 inch. And then we cancel the units. And then we can accomplish more complex versions using a sort of a step-by-step behavior. So for instance, if we want to convert kilopascals to pounds per square inch, or PSI, we start by multiplying by 1,000 to get pascals, then we take the definition of pascals to give us newtons per square meter. And then we multiply by the conversion factor between pounds of force and newtons, and then we take the conversion factor between meters and inches, and then we square it because we have meters squared. And then we can cancel all our units, and we're left with pounds force per inch squared. And if we put all the calculations together, we get 14.7 pounds per square inch, or psi. So this gives us atmospheric pressure. It's 101.3 kilopascals, but it's also 17 or 14.7 pounds per square inch.